We're going to start from the efforts that Qualcomm has been putting into generative AI, and then look at one of the a cool demo that we recently showcased, where we run stable diffusion based ControlNet on device, on a mobile phone, in fact. And finally, we will also take a look at some of the research efforts that are going on within our company, where we have used diffusion models for image codecs. Let's start with the big picture of generative AI itself. I'm sure most of you might have are fairly familiar with this topic. I wanted to kind of start off with a more broader picture, and then we can zoom into a few other topics. What exactly is generative AI? It's a more modern term, I would say, quite recent. So we call generative AI as AI models that essentially create some kind of content in the form of, say, images or text, video, audio, and even code. For example, these are models that are able to generate this data. And we interchangeably use the words generative AI or foundational models or large language models interchangeably, but they kind of encompass within the same area. Recently, we have seen these models being used across multiple applications, starting from just text generation. You have models like ChatGPT, Bard, which take in an input prompt in the form of text and generate text that is relevant to your prompt. And you already see a lot of applications coming out of this in communication, journalism, publishing. We already see a lot of articles which are actually generated by such models, and the application just goes on. Then following this, we have also image generation, so wherein models like Stable Diffusion and Midjourney, which take in a text prompt and generate kind of an image that is a response to your text prompt. And again, here it ends up finding its applications in advertisements and, of course, novel image generation and so on. And finally, we also see these models being used in code generation. So given a prompt, just a simple prompt, these models can also generate some skeleton code, or in fact, quite well set of code lines, which you can use for your web design, software development, in fact, even coding and so on. So the applications are limitless in some sense. You can you end up seeing being used right from text all the way to something as niche as generating code for your applications. When you look into particular applications itself, they might also be they are also device specific. You not only need these models to do well, but you also need them to do well on a particular device, for example, and that opens up a whole range of new options. Starting from XR, for example, generative AI can be used to generate much better 3D scenes, which are richer and perhaps emulate the gaming experience much better. Then you have automotive applications where generative models are being used to generate data that can be used to train these models, which essentially run autonomous vehicles. Then you also have phone applications, which ties in from our previous from the previous slide, where you have text-based prompts and you generate some kind of visual or text data relevant for the user. You can also generate slides using these models, and finally, you also have productivity improvements, because not only code-based generation, it can also be used in several IoT-based applications. So we kind of see that not only the applications, but this generative AI will be quite prevalent across many devices. If you were to zoom out a bit more, we end up seeing that the whole technology itself is quite transformational. It has a broad set of applications. It can create content in seconds, and as you can guess, it has a huge potential for revenue. We already see ChatGPT being one of the fastest growing applications, and a bunch of plugins have been developed for ChatGPT. And in terms of revenue and economic terms, there's a lot of investment in this field. There's a quite drastic increase of VC investment in generative AI, and a huge chunk of market size that will belong to this technology. There's a huge potential, but the same potential comes with a few challenges, as you can say, because uh, these models, generative AI models, are massive models. They are billions of parameters, and they require huge compute. They require a lot of memory. For example, models like, say, Stable Diffusion in one of their earliest versions would take a long time to generate a single image, and the time could also reach a few minutes, for example, which is a lot of time if you think about a low-level application like on your phone or on your PC. It's not practical in terms of applications itself. So there are a bunch of challenges that these models bring, and in order to kind of make them practical, these challenges need to be addressed. So these challenges that I was talking about, at Qualcomm, we address them across different axes. For example, running generative AI on device is itself a challenge, because the hardware needs to be optimized for it, and we need to figure out how these models can be ported on device, such that they don't, for example, heat up your phones, or slow down or eat up too much data, for example, or maybe slow down the phone itself, or any other device. And then there are algorithmic developments related to this, which actually forms quite an important, almost a crux of these models, because these algorithms, for example, the diffusion-based models or LLMs, these algorithms can be optimized for the specific application, and they can also be optimized for space and even runtime efficiency. So a lot of optimizations can go on even in the algorithmic axis. And finally, you have software tools. We also develop software tools which accelerate the runtime for all kind of deep learning models. We have multiple SDK or development frameworks which enable such development. And overall, it's a more wholesome way of building power efficient AI, and it's optimized across different axes. I will talk about a few points a few applications that are already out there from Qualcomm, which encompass these three axes. One of them is is within our XR area, where we have made a lot of progress in building power efficient AI. And at the same time, we also have some software development, software related applications which enable models to be ported onto device. So within XR, we've developed something called as Snapdragon spaces. And you can see that we kind of we go across all the three axes. We have platforms such as Snapdragon platforms, both in different generations, each being better than the other. And we have developed particular algorithms for various XR related applications, such as object tracking, eye tracking movements while you're wearing these head glasses, and hand tracking movements, and so on. And also we develop reference designs based on which the industry or our customers can basically catch up on these on how these devices could be used. And finally, all of these is encompassed within the Snapdragon spaces, where people can contribute and basically take it from there. Yeah, it powers a lot of devices. We have around 60 plus devices which have been launched, which are powered by Snapdragon, and a bunch of AI technologies that are used within these devices. And this has actually launched the whole metaverse related application itself. For example, the AR glasses are one application, and essentially we have launched a huge metaverse. These devices basically open up a whole new avenue for the whole metaverse application itself. So that was related to the XR area, where we have already advanced quite a bit. We already have applications which devices which are powered by these technologies. And on the other end, we have a toolkit called as AIMET, which essentially makes AI models small. So what do I mean by that is, so we have usually deep neural networks are quite large models, and you can imagine that porting them on device is quite expensive, and running them on device is quite expensive. So a toolkit like the AI Model Efficiency Toolkit essentially does two main operations, which is compressing these models, so making the weights, uh, so essentially reducing the model weights itself. So you could, for example, imagine removing some of the connections within a fully connected network, and still the network performs pretty well. So essentially you're removing connections, and as a result the model is smaller, and but still the performance is maintained. And at the same time you have quantization, wherein you are uh, usually the weights are represented in the form of 32 bits within a hardware, but you could reduce the number of bits being used for the weight, and uh, as well as the mid activations within a layer, reduce the number of bits that are being used, and thereby you are also again compressing or rather reducing the amount of space or memory that the model occupies on a device. Uh, so finally, after these operations, you come up with an optimized AI model, which which, as I mentioned, has lesser number of weights perhaps, and also has weights which have been quantized. And all of these operations are done in a manner that does not affect the model performance itself. So they are optimized for model performance, and eventually these models are deployed on devices. So what are the features, and what exactly constitutes within AIMET? The benefits of using these toolkits are many. So you're going to come up with a model which has lower power, it has lower memory bandwidth, it maintains, like I mentioned, good model accuracy. Eventually, the model will require lower storage, and another added benefit of such a toolkit is that you could optimize your model in such a way that the model performance actually improves. So you could train the model with during quantization. So there's something called quantization aware training, which you could do, and still continue to improve model performance. And overall, it's developed by software developers, so they made sure that this toolkit is easier to use. Within the quantization setup itself, like I mentioned, there are multiple operations. So there's something called quantization aware training, wherein you train the model when you're quantizing. So you quantize the weights, run a model forward pass, generate the output, and then train the model such that it matches your ground truth, while it's optimizing also for the weights. There's also the other operation of post-training quantization. So once you're done with training the model, you decide that that's your final model, and then you decide to quantize the weights. And there also we have some very state-of-the-art techniques, such as adaptive rounding, mixed precision, auto quant, and so on. So yeah, definitely take a look at the GitHub page for this for all of these techniques. Finally, if you would like to compress these models, that is reduce the reduce the number of model weights, we also have techniques to do that. One way to do it, for example, could be, say you have a neural network which generates its hidden states and generates many channels in the hidden states. You could consider reducing these number of channels. We observe that actually pruning away some of these channels doesn't really harm the model performance, and you still maintain a leaner model but good performance. So that's just one of the techniques that you could consider for compressing your models. And finally, this is a toolkit. This helps you visualize gives you a lot of insight while you're doing this, so that you are not just flying blind. You are directed by some visualization of how your weights are changing, how your model is performing, and if you wanted to quantize your weights, what kind of ranges you need to choose. You could consider compressing different layers at different ratios, at different compression ratios, and this model also shows you, gives you this setup also gives you visualization of these ideas. So it's a more wholesome way of quantizing and compressing your models, which is quite important if you plan to run them on devices. Using such ecosystems such as AIMET, we have shown a bunch of demos where we have shown devices running models, running neural networks on devices. One such application is super resolution, where we show this demo at 100 plus FPS. So FPS is frames per second. So we actually process 100 plus frames per second on a mobile phone. And what I mean by super resolution is that given a low resolution image, you run it through a neural network that essentially adds more details to the image, and the super resolved image will now look much cleaner and crisp. This is actually an 8-bit, so instead of a 32-bit model, we create an 8-bit model using our AIMET toolkit and using this quantization aware training. And eventually this model, which was quite a huge a huge number of parameters, was ported on device. That was just one of the demos that we showcased a year ago. Following this theme, we also of course could not shy away from running generative AI models on device. And one such generative model is called ControlNet. I will talk about what ControlNet is and how exactly it operates. And this was the first on-device demo of ControlNet, which we showed running on a phone. This was actually a 1.5 billion parameter model that runs efficiently, and you can actually interact with the model. I'm not sure how familiar you are with a stable diffusion, but usually diffusion models require you to sample from it for at least a minimum of 20 diffusion steps, or let's call it inference steps. And in fact, at the time when this demo came out, people were sampling these models for at least a minimum of 50 diffusion steps. We were able to bring this down to 16, so that's quite a big jump. And we were able to do the inference in just 12 seconds. What is the biggest motivation to do this is you can imagine that running models on devices, processing data on devices, gives you better security and reliability. Your data stays on device, so there's less threat related to privacy. All of this was kind of built using the whole Qualcomm AI stack. Given an input image, what happens with the ControlNet demo is, given an input image and you give an input prompt, say that you want a yellow kitten and a photorealistic version of it at 4K, which is quite massive resolution. And given these two inputs, the ControlNet model basically generates an image. The ControlNet model, uses conditioning in the form of an image and a text prompt. So it borrows from Stable Diffusion model and then adds a block on top of it, which we call ControlNet. So let's start first with what is within the Stable Diffusion model itself. It is essentially built to, given an input prompt, it generates an image for you, which answers that prompt. So in this case, let's consider just the blue set of blocks within this diagram. Let's consider the blue regions, which is the Stable Diffusion model itself. So given an input prompt, which in this case is a was in Greek style with intricate patterns and design. So this is a text prompt, and this goes into a module called as the clip text encoder. So this encoder generates a latent representation or an intermediate representation of the text itself. And these are massive. This is already a big encoder. It's 123 million parameters worth model, and it generates a latent representation of this input prompt. And what we have and what forms an important part of this stable diffusion model is an architecture called UNet. UNet, you can imagine that literally is a deep neural network which is in the shape of the letter U. And this is actually quite a big chunk of stable diffusion because it's 860 million parameters. So you can imagine that a lot of compute and a lot of multiplying addition operations, or what we call as max, go into this module. And this model receives as input this latent representation of the text, and at the same time it also receives an input from something called as a scheduler. So I will go into a little bit of details of what the diffusion process is in the later part of my talk. But for now, you can, if you're not familiar with diffusion, you can think of it as a module that outputs something called as a time step. Since the model is sampled sequentially, you go from 0, 1, 2 till say 100, and each index in this range is a time step. So this time step is also being input to the UNet. It needs to be aware of where it is in the trajectory. So for now, just think of it as some time step which is converted to some latent form and introduced as an input to the UNet. Finally, the UNet generates another latent representation, which is sent to this decoder. Decoder finally generates an output image. So this is what happens within Stable Diffusion. So this is how it processes your text embedding and generates an image which answers the text embedding. So that's the Stable Diffusion part. Now, but you can see that it generates an output image. But you could consider modifying this output image, and that's where ControlNet came in. What this model does is that it adds another layer of fine tuning. So it's actually built on top of Stable Diffusion. So you always start off with a pre-trained Stable Diffusion model, which is open sourced, and you build on top of it using a ControlNet. So a ControlNet model has another encoder, so which pretty much guides the generation process. So this is a small, compared to the UNet, compared to the entire module, it is a 390 million parameter model. And it receives as input the text embedding and a reference image. This extra conditioning, which you see on top, input image, can be of any form. You could consider giving some kind of a semantic map, or some kind of uh, uh, class conditioning. People have experimented a lot with this type of conditioning, and there are various types of control nets out there. In this case, we consider just a single, just an input image of the type that we want to generate. And the control net encoder receives as input all of the text encoder, the time step embedding, and also the extra conditioning. And now the UNet and it provides this control net. Let's call this control net conditioning is provided back to the UNet. So now the UNet has some more extra information that it uses to generate an output that is of the form that you would like. So essentially, the idea of ControlNet is to steer, or rather move. Let's use the word steer. Steer Stable Diffusion in a way that you can generate images or modify images or edit images the way you would like, to. And all of this comes from this control signals of this input image and this and an input prompt. This kind of serves as a very nice, this, you can imagine the applications coming out of this. You can do in painting, you can do editing, you can do any kind of generate animations out of this, whatnot. So this is the model that we end up optimizing and porting to device. So our Qualcomm AI Studio, or as what we would like to call it, is this entire stack which kind of goes into getting things to work on device. It starts at a very low level. It works all across different OS, starting from Ubuntu to CentOS and whatnot. We also have system interfaces And we also have a different at different layers. We have a different optimization stack, which is specifically tuned for this device for this model. And finally, what's relevant for us is the Qualcomm AI engine direct, which actually uses these AI frameworks and essentially we are able to run different AI frameworks like TensorFlow, PyTorch on these devices. So you have models coming in, and we bring them within our framework such that we can run them on device. And all of this can be handled with our SDK toolkit as well as our using the AIMET toolkit. This is what we ended up using. So the entire full stack optimization for ControlNet was when I as I spoke about the quantization part of it, we used AIMET, wherein we used 8-bit quantization to actually quantize the model, and we also used the Qualcomm AI Engine Direct to for the improved performance and to actually minimize memory spillage. By what I mean is when we are moving tensors across different hardware components. We used our toolkit, which is Qualcomm AI Engine Direct, to avoid any kind of spillage during such operations. We also used our hardware acceleration, used our Snapdragon 8 Gen 2 mobile processor for this. All of these it forms a complete recipe for optimizing ControlNet overall and actually bringing down the latency to just 12 seconds. So what we end up seeing examples are editing is quite a common application for this for ControlNet. So given a reference image and a reference prompt which specifies how you would like to edit the image, you end up with different generations from ControlNet. And this of course, because this is a noise-based model, this gives us different versions of a similar image. So here, the Evenness canals is what images on the right show, but they show different versions of it when you sample every time. So you get some diversity out of it, but the fidelity, that is, it still continues to show you the Evenness canals, but in different form. So what we at Qualcomm see is that on-device AI can actually support a variety of generative AI models. It does not stop at ControlNet. For example, ControlNet itself was like a quite massive model, and we already see it on device. And as of now, we already see a lot of papers and research being done to reduce this runtime even further, reducing it down to, like I mentioned, 16 inference step. People have reduced it down to 8, 4, and with very good quality. The quality drop isn't significant. So there's a lot of progress happening in that area in terms of reducing inference time. And also along the axis of reducing model size itself. For example, you see PaLM, which is a large language model, and it's I think it's 7 billion parameter model, and it's already quite on par with some of the massive large language models. There has been research going on along both the model size as well as the inference time for these models. We see that getting these models on device and across different areas, be it NLP, text to image applications, is actually is happening quite fast. This we can run 1 billion parameter models today and anticipate that growing to at least 10 billion in the future. So now we kind of move into a more research topic. This is a topic that my team and I have been working on at Qualcomm. We have our paper on archive at this point. It's called a residual diffusion model for high perceptual quality codec augmentation. That's quite a mouthful, so we call it DIRAC. This is a joint work with my colleagues here, Jens, Auke, Chanlin, and Guillaume. For this talk, we will also look into a few basics. So you can a few basics of diffusion process and some more basics of image codecs, and then we will go into the method itself, and finally you can take a look at some of the results of this model. I think many of you will be familiar with JPEG. It's a very common codec. It essentially compresses the images. On the left-hand top, you see a cat image which was compressed by using JPEG. this was compressed to like 12.8 kilobits per second. And you can see that the quality of this image is quite coarse. It's very blocky and a lot of artifacts, not great to look at the eye. What DIRAC does is enhances this image. So to the right, you have JPEG plus DIRAC. That is our model applied on DIRAC. And it maintains the same bitrate, which is 12.8 kilobits per second, but it improves perceptual quality. There are two metrics by what we measure this improvement in quality. Of course, there's visual feedback, but we also use something called PSNR, which is peak signal to noise ratio. Essentially, it measures the amount of signal that actually exists, kind of a distortion metric that tells you how close your image is to the ground truth. And in our case, we actually improve this PSNR. We get much closer to the ground truth. And there's another metric called FID. I will not go into too details of what this means, but you can consider it as a proxy for perceptual quality. And what I mean by that is how good the picture is to look at. And FID is a common metric which is used within the codec, or rather the diffusion community as well, to measure quality of generated images. So JPEG is one of the is a more earlier codec, but of late there have also been a lot of neural-based codec. So what I mean by neural-based codecs is you use deep neural networks to build models that compress images. Here also we see that the image on the bottom left is generated by such a neural codec. It's a counterpart of JPEG, so something that competes with JPEG. So it's definitely better than JPEG, but it still lacks details that, for example, the hair here is not that great to look at. And what DIRAC does is that adds more details to this image. But now here we see a drop in this PSNR compared to what the base codec gave us, but we see improvement in visual quality. So there are a few trade-offs here, but overall, the images on the right, the two on the right column, kind of show you the effect of using DIRAC on such codecs, and this is actually a diffusion-based model. So DIRAC enhances the perceptual quality of any base codec, a standard codec or a neural codec. What do I mean by perception and distortion? So you saw that I was talking about PSNR, I was talking about FID. At a much simpler level, what do these really mean? Our codec, which is DIRAC, it optimizes for both perception and distortion. So consider that you have an original image, which is the leftmost image. And if you were to optimize this for rate and distortion, that is, you optimize it to have some bitrate and some level of distortion. So you would like it to be very close to the ground truth, and you would like to use as few bits as possible. What we end up seeing is that it is fairly close to the ground truth. The basic structure looks quite close to the ground truth, but as you can probably see, it's quite blurry. Not that fun to look at. Like if you were to display this on a screen, then this is not that great to look at. So in this case, you have, so in the third column, you see very good perceptual quality, but fairly bad distortion, or it's not close to the ground truth. So you can imagine what this entails. If you were to optimize just for perceptual quality, say you send an image which looks like second column, which is a blade of grass, but what you receive at the receiver side is the third image. It's much different from what was sent. That's definitely not what you want when you're compressing data. You don't want to compress files and then when you uncompress it, you don't want the data to change. But in some cases, you might be okay with actually the data changing. You might want the images to look crisper. But in data, for example, related to text or images which are important to you, you would not want data to change. So there is this trade-off that you might already see. So you can have very good fidelity. You can be very close to the ground truth, or you can be very far away from it. But there is probably a trajectory between these two, where you could trade off distortion, and perception. So our model does exactly this. So it starts off with distortion, which are these blurry images, but very good fidelity, and traverses all the way to a very good perceptual quality. And as a user, you can actually modify or basically traverse this trajectory the way you want. You may want high perceptual quality, sure, uh, or you may want very good distortion. That is, you want to stay close to the ground truth. Then you could also the model can also do that. So our model traverses this trajectory in a using this diffusion process itself. So, coming to some top results from our paper, we show this trade-off between fidelity and perceptual quality using the diffusion model's sampling schedule. We have a top competitors. So you might have heard about a lot of GAN-based methods, generative adversarial networks. They also do quite well here in this space that we are looking at, and we obtain competitive quality compared to these papers. We show that we can apply our solution to multiple codecs. So as you saw in the beginning, we applied it to JPEG. We also applied it to a neural codec. Finally, we also show that we can improve this sampling schedule. So initially, when I was mentioning inference step, if you recall, during the number of time steps that you sample a diffusion model for, using our paper, we also show that we don't need more than 20 sampling steps to maybe do this. So before we go into how we actually built this model, I will give a small background on codecs and a small background on diffusion process itself. So what is a codec? Um, Essentially, it compresses an image, and a neural codec uses something called as an encoder, a decoder, and a prior. Given an input image X, you have a latent, you encode it and generate a latent Y. This latent Y is encoded, which basically serves as our rate. So it decides the number of bits being spent to, for example, transfer this image to from the sender to the receiver. And at the receiver side, you have a decoder which receives this latent Y, and you decode it and generate a reconstruction X hat. And to train such a codec, you train it using a loss, which essentially measures, for example, you could just measure a mean square error loss, which we call as distortion loss, and you have a rate loss. And when you're training this model, it's you optimize for both rate and distortion. So the previous slide was the usual way of training these distortion models or high fidelity models. But a lot of papers have explored doing something called as perceptual enhancement of codecs. So you add an enhancer on top of at the receiver side, and this mod and add a loss term called as a perception loss. Usually, this loss is sometimes GAN-based loss, or it can also be something called as an LPIPS loss. So there are different things that people have experimented with, but some of the most successful models have been GAN-based, and there's a GAN loss usually which is added on top of the distortion and rate loss, and the model is now optimized for it. So that's a very brief summary of both distortion and perception based codecs. But it turns out that you could actually do better. You can maybe do better than GANs at this point, especially given that diffusion models are so common now. So I wanted to go a bit into what exactly happens during diffusion and how this will eventually tie into our work. So let's look at what exactly is diffusion. So you start off with some data that you have. Let's call this x0. Define a diffusion process which slowly starts adding noise to your image, and it is done very incrementally. So you can see incrementally the image being turned into fully noise, and you reach a point x capital T where the final image is just pure noise. So you start from data and you go to noise, and this is referred to as forward process. In the reverse process, you could imagine starting off again with some noise, and then you go back, you follow back the trajectory and generate back the data from it. So what we learn is, or what we train the neural network to do is denoising. So it learns to denoise from noise back to data. The reverse process, which is generative process, and forward process is always fixed. This forward process is controlled by the amount of noise that we end up adding, and usually this is called as a noise schedule. So you decide the amount of noise that you're adding at every time step and the type of noise that you would like to add. So usually, in a lot of diffusion models, you'll see cosine noise schedule being used. So essentially, this is on the x-axis. So you can see the plot on the right-hand corner. You see the diffusion time step. So the time step here, I mean, at x0, at x1, x2, so on till x3. So at every time step, you add some amount of noise, and you basically define and at the rate at which you would like to add this noise. And this parameter is controlled by something called as beta t and sigma t square, which controls the amount of noise that you add and how you add it. And yeah, the usually linear and cosine schedules are used commonly to do this. People have experimented with a bunch of different noise schedules, but uh, I think linear and cosine have stuck along. To train such models, so to train such reverse process, this is learned using a trainable network such as UNet. So what the UNet learns to do is learns to predict the latent at time t minus one given the time t, and generally, I'm not going to go into details, but what is generally learned to predict is the noise. So what we learn to predict is starting from time step, for example, in the slide, starting from time step x3 to x2, the model learns to predict how much noise has to be removed from the model uh, to uh, to denoise it. So usually the loss is based on something called as epsilon, and these are noise prediction networks. This is a very common parameterization of diffusion models. In our paper, what we end up doing is that we predict x0 directly. And by that, what I mean is, say, for example, you are at time step x3. At time step x3, you learn to predict what was x0 that gave rise to x3. So this is called as x0 parameterization. And we found that this actually works much better for us than the usual epsilon prediction. We looked at what the diffusion process was, what the noise schedule was, what loss parameterization we have used, and now we look at the conditioning that can be used. So generally, diffusion models are trained in a conditional manner. That is, you use some kind of extra information that can enable the model to learn the process better. So in the case of ControlNet, you might recall that we used text conditioning and image conditioning. In our case, we also use an extra conditioning parameter called as C. So what we do is we run our image codec first. So we encode the image and decode it at the receiver side, and you generate an image which may look maybe blurry, for example. It's distortion optimized, so it will match the ground truth, but it may not look that great. And that reconstruction is used as a conditioning for our model. And we start from there, and we try to generate the full trajectory from distortion to perceptual quality. And then finally, we have the sampling process itself. Now, like I mentioned, you start from time zero and you go till time step capital T in the diffusion process. And when you're doing a reverse process, you start from capital T and go back to time step zero. So starting from capital T and going back to zero is the reverse process. So it's a reverse sampling process. And turns out that after training the diffusion model, you can actually apply various types of these sampling techniques to generate an image. So people have experimented with this quite a bit. There are starting from something called as DDPM schedule sampling to now to DDIM sampling. People have also used solvers. All the goal of these sampling techniques has one of the goals of these sampling techniques has been to reduce the number of steps. So although you may have trained for 1,000 steps, you can sample just for a few steps and generate images out of it. And one such technique which does this is called DDIM sampling. So essentially, it is used during inference time. So after we've trained the model during inference, we can change the type of sampling process that you use. We train for 1,000 sampling steps, but we sample using 100 steps, and then we later also show that we can just use 20 steps. That is just 20 times going to, 20 time steps in the trajectory to generate the real image. And DDIM is still commonly used for sampling, although there are some newer techniques like DDPM multi-step solvers. So now coming to the actual architecture of DIRAC. So DIRAC starts off with a base codec. So the base codec can be any kind of codec. It can be JPEG, it can be and it can also be any other type of neural codec. Given an initial original image, it generates a reconstruction. As you can see, the reconstruction is not that great to look at, but it's still a cat, so that's good. And it's conditioned on some rate. So that rate defines the number of bits that you spend to send this information. So this initial reconstruction forms our conditioning. We then run our diffusion model. So this diffusion model is run at the receiver side. So you have generated an initial reconstruction, and now you're going to run a diffusion model on top of it. Given the initial reconstruction, which is in our case X tilde, we condition the diffusion model on this X tilde. We start off with some random Gaussian noise, and we do a reverse sampling process. So we generate an image, but instead of generating the final image, what we generate is something called as residual. And what we mean by residual is essentially the difference between the original image and the initial reconstruction. It's just literally just the difference between the original image and the initial reconstruction. We found that training model using to generate residual is actually much cheaper. It was faster and gave us a lot of benefits during training. So it did not require a lot of training compute that would otherwise go into training a model to generate images. Although theoretically, this shouldn't have a big difference, but practically, we found that training a model to generate residuals was much easier than training it to generate the final image. So our diffusion model runs this reverse diffusion process, which is conditioned on the initial reconstruction and of course the diffusion time step, and it generates the final residue. Now, once we have the residue, we add this back to the initial reconstruction because it's the difference that we were looking for, and we generate the enhanced reconstruction here. This enhanced reconstruction is perceptually better pleasing than the initial reconstruction. Now, as you can see that adding the residual back to the initial reconstruction modifies X hat, or our enhanced reconstruction. Depending on the number of sampling steps that we take, it determines the final quality of our enhanced reconstruction. So if we were to follow the complete trajectory from noise to the residual, then we reach high perceptual quality. But if we were to use less than, for example, in this case, half the number of sampling steps than what we define, then we get a residual which may be blurry looking, but it still does not, it may not be high perceptual quality, but it will be fairly good fidelity, or it matches the initial reconstruction fairly well. The diffusion process itself allows us to trade this off, because going from noise to residual, it's a trajectory which allows us to trade off fidelity and perceptual quality. A few results of how this model performed, or how this method worked for us. So I realized that the x-axis is unfortunately missing the label here, but the x-axis here is the bit rate. So it's the number of bits that you spend in sending the information. On the y-axis, you have PSNR and FID. So as I mentioned, PSNR measures the distortion between two images, that is the ground truth and the generated image. And FID is a more perceptual quality metric. So what FID measures essentially is how close two distributions are. So in our case, we have a test data, which in our case is click test full res. It's a bunch of images, which I think are around 400 odd images, which are very high resolution. And we measure how close our generated data of 400 images is to the ground truth 400 images. So FID is distance measuring metric, whereas PSNR measures it as per image. So for every image, we measure what is the difference between the ground truth and the generated images. So DIRAC is a metric, is a model which traverses both distortion and perception. Now, in the plots, you see some orange, you see an orange shaded curve. So starting from, yeah, another point to mention is that you would want to have lower FID, but higher PSNR. By what I mean by that is you would want the distributions to be closer to each other. So you want the distance between the two distributions to be as low as possible. So that's FID should be lower. And you would want the PSNR to be higher. So you would want the signal, the amount of signal in the information to be much higher than the noise. And yeah, so what you see here is the shaded region, and you can see that FID is the model basically traverses FID quite considerably. So you can start off with low FID and go to very high FID. Low FID implies good perceptual quality, and high FID is not so great perceptual quality. And we do this for several bit rates. We get closer to quite some of the biggest competitors that we have for this model, including Hi-Fi C and multi-realism. When we have DIRAC 1, which is we just run one sampling step, so you can imagine that it may have very good fidelity, but it may not be that good looking image, so it may not have great FID. That's exactly what we show. Doing one sampling step, we have very good PSNR, but lower FID. But when we have good PSNR, we match some of the state-of-the-art results. When we and DIRAC 100, which is 100 sampling steps, so you actually spend a lot of compute to generate these images, and we perform equally well to multi-realism, which is a GAN-based method. And also Muckley 2023 is also a GAN-based method, and it actually achieves the best FID amongst all the methods here. Having a low FID is good. It's again a proxy metric, so it may not really mean that you have a good perceptual quality. And what I mean by that is perceptual quality turns out to be very subjective. An image may have very low FID, but is perceptually not very pleasing. So as I mentioned, MS ILLM, which is by Muckley, performs much better in FID. But when we were to look at some of the images generated by this model, it actually loses some fidelity. So in this case, in this example, on the left-hand top side, you see a ground truth image, which has some text on top of it. And on the right-hand top row, you see the generated image by the method MSILLM. It loses some fidelity in the text regions. Whereas in case of DIRAC, even though we reach the top perceptual quality, which is DIRAC 100, we see that there is more fidelity maintained by the model compared to the models which have higher performance, but the fidelity is still maintained. We kind of covered all the points here, so we see that we are able to trade off this distortion and perceptual quality using the sampling schedule. We also achieve competitive perceptual quality to a lot of GAN-based methods and also some diffusion-based methods. We applied our solution to various codecs, and we also reduced the total number of sampling steps that were used at test time. Yeah, that kind of covers the paper. You can check it out on archive. I will post the link to it. And yeah, if you have any questions, feel free to reach out to me.